let's re-explore a topic that I brought up back in Chapter 4, which is the fundamental equations of internal energy and entropy. And so, to derive these equations, you remember that we considered a closed, reversible expansion or contraction of a single component and single phase system. So something that's in, one type of molecule that's either completely gas, completely liquid, or completely solid. Okay, and it's undergoing a reversible expansion or contraction. Okay, and so for this sort of system, the first law was dq plus dw, and since it's undergoing a reversible expansion or contraction, we could rewrite the work as minus pdv. For the second law, we had ds is equal to dq over t plus s gen. It's reversible, so s gen is equal to 0. That's just equal to dq over t. If we rearrange the second law, we get that dq is equal to tds. And therefore, if we combine the first and second law, what we get is that du is equal to tds minus pdv. And this is what we called the fundamental internal energy equation. Okay? Just combining the first and second law. So we've seen this before, but now I kind of want to talk about this in a more mathematical way. All right, and so if we take a look at du, we see that it's equal to two different terms here. Yeah? All right, and these terms, these pairings that we have temperature, and then in the derivative, we have entropy. And over here, on the right-hand side, we have in the derivative volume, and the coefficient here is going to be negative pressure. So the sign there is important, okay? All right, and so we have in this fundamental equation TdS minus PdV, where it tells us that changes in U are going to be affected by changes in entropy and changes in volume. Okay? And so what we say here, when we have this sort of structure for our equation, is that our internal energy is going to be a function of S and V, where S and V are what we call the canonical variables. Right? And so that's just a kind of a special fancy term. Canonical is just saying these are the variables that are in the derivatives when we take a look at the derivative of this function. All right? That's all that's saying. So if du is equal to a function where we have ds and dv, that means that s and v are the canonical variables. Okay? Right? So that's, what the canonical variables mean. I also want to talk about these pairings here, because they also have special names. I want to make sure I get the sign there. Okay? And so this first pairing that we have for du, this is called the thermal conjugate pair. Okay? And so the conjugate pair, that refers to whatever the canonical variable in the derivative is, along with the coefficient that's out in front of it. Okay? And so we call this the thermal conjugate pair because it's dealing with temperature. On the right hand side, this minus PdV, we call this the mechanical conjugate pair, where V is the canonical variable, and then its coefficient is negative P. Right? And this one's called the mechanical conjugate pair because it's dealing with mechanical work or changes in volume, changes in the size of the boundary of the system. Okay? All right, and so we'll talk more about, why knowing these thermal conjugate pairs or why knowing the canonical variables are useful. But another mathematical thing I want to point out is that, if I'm saying that internal energy is a function of S and V, then if we took the total derivative, just mathematically, if we took the total derivative of U and wrote it in terms of its partial derivatives, we would write it like this. Okay? And so just to be clear here, the internal energies and the entropies that I'm writing here, and even the volumes, these are all intensive properties, right? So you could either think of the molar versions of all these, or even the mass versions, the specific versions. But for at least just kind of clearing up the notation, I'm just not going to include them right now. Okay. In any case, right, if we take the total derivative of U and just wrote it out, just like treated it just as a pure math function, this is what the total derivative would look like in terms of partial derivatives. Right? This is interesting, this is useful, because if we compare this to this, they look almost the same, right? du on the left here, then we have a ds and a dv. Right? And so, by inspection, what this would suggest is if these two things are equal, by inspection what that would suggest is that this partial derivative of U with respect to entropy is equal to T. So from direct inspection, du ds at constant V is equal to temperature. And also, by direct inspection, du dv at constant s, which is the coefficient in front of dv here, that's going to be equal to negative p. Negative pressure. And the reason this is important is because now we have these partial derivatives of internal energy and entropy, things we can't measure. We're now directly relating them to things we can measure, like temperature or pressure. So from this fundamental equation, just looking at it, just inspecting it, we're able to relate, molecular properties to actual measurables that we could, comprehend. Okay? All right, and so that's what, the analysis of the fundamental equation for internal energy, that's the sort of insight we gain by, in using these partial derivatives. We could also do the same thing with the fundamental S equation. Do this with S. Okay? So for the fundamental S equation, which is 1 over t du plus p over t dv, if we take a look at this, for ds, we see that the derivatives here are u and v. And so this would tell us that S is a function of internal energy in volume. If we wrote out the total derivative of S in terms of its partial derivatives, we would get this. And once again, by direct inspection, if we look at the du term, if we equate these two things, we see that the coefficient in front of the d term would tell us that the partial derivative of ds with respect to u at constant v is equal to the inverse of temperature. Okay? That's consistent with what we got from the fundamental u equation, where we had du over ds at constant v is equal to t. Here we have ds over du at constant v is equal to 1 over t. And if we remember the reciprocal identity with partial derivatives, we know that ds over du is equal to du over ds. Hence, that's why we get 1 over t. Okay? And also, from direct inspection, if we look at the terms in front of the dv, we see that ds dv is going to be equal to p over t. Okay? All right, so once again, we're able to at least relate molecular properties of entropy and internal energy to things like temperature and pressure. Right? Of course, if we go back to our motivating factor where we wanted to figure out what ds dt and ds dp were, these are interesting. But we don't quite have the partial derivatives that we want. Right? Because we wanted things like this. All right, and so, looking at the fundamental equations does give us insight, but they're not entirely, they don't give us all the information that we need. So we're going to need a few more tools.